webcast continues in Worksheet 7F and looks at problem 8. Okay, so this problem 8 is talking about a satellite in orbit above the Earth. Because they're giving us, or they tell us to assume that the satellite's orbit is circular, they're giving us the altitude as 700 kilometers above the surface of the Earth. Okay. The first question is, what's the orbital velocity? So I know that the formula for orbital velocity is the square root of gravitational constant g times the mass of the larger central body divided by the orbital radius. Maybe I should calculate the orbital radius here. That should be the radius of the Earth plus the altitude. And I need to put this in meters. So that's going to be 6.38 times 10 to the 6th meters. That's the radius of the Earth. Plus the altitude is 700 kilometers. So that's 700 times 10 to the 3rd meters. And if I add those, I get 7,080,000 meters. Okay, so that's our R. So now we can find this orbital velocity. It's going to be the square root of g times the mass of the Earth, because the Earth is at the center of this satellite's orbit. It's the bigger mass, and that's the one that will determine the velocity of the satellite. And then I put the orbital radius that I just found. Okay. And I get a velocity of 7,499.52 meters per second. Okay. Then it asks the gravitational potential energy of the system. So that's E sub g. And the gravitational potential energy of a satellite is always negative. So I know there's a negative in this formula. And it equals the universal gravitational constant times the product of the masses divided by the orbital radius. And so we could find this. And it equals 5.512 times 10 to the 11th joules. Okay, then it asks, what is the kinetic energy of the satellite? Well, the kinetic energy of a satellite is always positive. It would be g times the product of the masses divided by 2 times the orbital radius. But if I compare the kinetic energy formula to the formula for gravitational potential energy, I see that this should be half of the absolute value of the gravitational potential energy. So I don't really need to plug those numbers in and calculate it again. I'm going to take what I found in part B, I'm going to divide it by 2, and I'm going to make sure that the sign is positive. Uh-oh, it's 2.756 times 10 to the 11th joules. And then the total energy of a satellite equals the sum of the gravitational potential energy plus the kinetic energy, or it equals negative g times the product of the masses divided by 2r. Oh, so if I just look at the formulas here, that must be the same amount that I just found as kinetic energy, except the total energy of a satellite is negative. Okay. Then, part E, we're looking at how much energy would it take to move this satellite to a different, higher circular orbit. So the original, the initial orbital radius was 7,080,000 meters. Now this new final orbital radius would be the radius of the Earth plus this 1,200 kilometers, so 1,200 e to the third meters. And so we're going to have a different it's going to be 7,580,000 meters. Okay, so to find the energy that's required, I have to find the change in the total energy of the spacecraft. And that means it's going to be the final total energy minus the initial total energy. And I know the initial total energy, that's what I found in D, right? So it's going to be negative G(m) over 2RF minus that total energy in the initial case. That's what I found in part D. Okay, so I can do this. Putting in the product of the masses here, divided by 2 times that 7,580,000 meters. Okay, so let me find that. Gravitational constant times the product of the masses. And then dividing by that new orbital radius, actually dividing by 2 of that orbital radius. Okay, so I have a final total energy of negative 2.574 times 10 to the 11th, and I'm going to subtract my initial final energy of 2.756. Oh, and that's negative 2.756 e to the 11th. And so I have a negative number plus a larger number, right? Because the minus gives me a plus. And so I find that it takes 1.818 times 10 to the 10th joules to move this satellite.